Hi there. Let's look at electrophilic aromatic substitutions, benzene replacing a hydrogen with an electrophile. In this case, electrophile will be attached in the place of any hydrogen because it's symmetric, and leaving side the mechanism. So we're going to look at how the benzene ring activation and deactivation takes place. So if I have an electron donating group, let's say D, and that will push electrons into the benzene nucleus, and you're going to see the pi bonds opens up in 3 different locations. So these ones can be numbered 1, 2, 3, 4, 5, 6, and where the negative will be sitting on number 2, 4, and 6. So we label 2 and 6 as ortho, and 3 and 5 as meta, and 4 as para. So simplified version is O, M, and P, or you can use the numbers. Now, as a result of this electron density difference, we're going to end up with one product, the electrophile attached to the para position or 4th position. The other one will be attached to the 2 or the 6, we call the ortho position, and the other one is attached to the 3 or the 5 based on the first attachment, and that would be a meta derivative. So that's how the labeling takes place, and we want to understand how the electronics work in this case. So if I have the electrophile EX, electrophile is a delta plus or plus, and the 2 electrons on the benzene acts as a nucleophile. So that's why this reaction takes place. Now, if we want to understand ortho and para, which is because it's those positions are negatively charged, that's why they take place. So when it is happening, because benzene is a nucleophile, it is considered as activating. The opposite is deactivating, because the 2 meta positions are not negative. They are not positive really though, but they are not negative, so these are deactivating positions. Now I kind of use this ranking system. It's like the number line, if you remember the redox that we talked about, similar way. So benzene is the standard 0, let's say, and then the methyl will push a lot of electrons to the ring. O methyl would push even harder, and the OH and NH even harder and harder. So it's a more positive or higher activation to the right. Now look at the left. In yellow, that's the deactivating groups attached. Especially you can notice there are double bonds attached to carbon or nitrogen, right? That's how O positive. So that's how they are deactivating. And fluorine and chlorine is a very special one. So let's not think about that at this point. So the deactivators are electron withdrawing groups from the nucleus, and the activators are electron donating groups to the nucleus. Now, fluorine and chlorine, even though they are electronegative, they can actually donate a bit of electrons. So that's they are even though electronegative. So it's a special case. We'll leave that behind for now, and let's look at how the production of 2 examples for each side, electron withdrawing groups, how they push a reaction, and then electron donating group, how they push a reaction forward. So if I have a double bond group attached to carbon or nitrogen, and that would be creating electron deactivators or ring deactivators. So therefore the electrophile is NO2 in this case. Look at that one. So this bond opens up, therefore the pi bonds on the benzene ring opens up that way. Therefore the meta positions will have a minor negative, smaller negative. That's why it's a meta directive or 3,5 directive. So your product, you would see as meta attached or 3 or 5 attached derivative. So that's because you had an electron withdrawing group attached in the first position, right? Okay, now in the blue electron donating groups, it's going to be different. So let's see, you have a CH3 group here that will push electrons to the ring, so it will enrich the electron density. So the more electrons, because of this push, this electron goes there, and you will have a negative charges definitely on ortho and para positions. So the NO2 electrophile attached to any of those positions, you're going to get one para product and two ortho products. So that's how the two products are getting after activating the benzene ring. So we'll look at the mechanisms in the next one. Thank you.